First thing, if you don't know, you have your first big homework set due, and it's due by 2 o'clock today at our review session in Fretwell 113, but I see a lot of folks go ahead and handing it to Joseph in the back. That's fine. Remember, you got to take this whole thing and don't forget to put the answers on Canvas site. So you actually have to come over here to the modules and then scroll down to your section, just past section 6.1 there. Test and test review. Here's your little link right here. Click on this thing. And you can get a copy of it here if you want to, but most important, you have to submit your answers on this. So I made it so that you can put your answers on the quiz here. And basically, you just go through each one and click it. Even the free response questions, I turned into multiple choice questions on this thing. However, that being said, what you guys are turning in for me today is just the free response section. So if you click on this thing, the first 15 questions are the traditional multiple choice, because I am trying to make this thing kind of mimic what my test is going to look like. So the first 15 questions are multiple choice, but then here's what I call part 2 of the test review, where I'll actually want to show some work here. Now these guys are basically whether you know the formula or not, pretty much all right, all wrong. I think I'll give you partial credit on this one, but the rest of these guys are just basic forms you're supposed to know. Then your fundamental theorem of calculus, and don't forget the label. That sucker's called f of x. That derivative is called what? F prime of x, or for you Leibniz fans, df over dx. Label your derivatives. And then this idea of total area. Total area, you want to graph this particular problem versus the concept of displacement. That's a formula. And then show me your techniques of integration and be very clean and concise in the way you write your stuff up and put your answers in the blocks and stuff like that. So I am trying to make this homework set mimic what I'm going to do for you guys on the test. And speaking of that, when is your test? Monday, that's right. So it's right here. This also means that your test 1 will be on Monday. So, and like I said, at 2 o'clock today in the review session, I'm going to be going over this entire thing, and I will record it, God willing, and then I will have this solutions posted here. So you know on your Canvas site, your Panopto recordings, it'll be here, is one place it'll be at, and I'll probably make a special link right below here on your homework set, so make it a little easier access for you guys. It's a great thing to study, get prepared for the test. All right, but we've moved on. We're in a section 6.3 called partial fractions, which is not going to be on your test. Your test stops at integration by parts. Integral u dv equals uv minus integral v du. That's going to be on your test, but the stuff we're doing on these breaking up fraction stuff is not on the test. So we're going to pick up where we left off. Remember, the idea behind integration by parts is to take one big fraction and bust them up over smaller fractions so you can make it easier for you to integrate. So, and we did all these problems last time for you guys, so let's pick it up where we left off. We left it off with this problem here. Now, they were nice enough to go ahead and factor this thing for me, but this was going to be a special case of partial fractions. This is the integral of 3x squared plus 5 divided by x minus 2 squared times x plus 1. Now, something new has been added to this guy, and that is one of your factors is actually to a power, okay? And when you have this case of one of your factors is actually raised to a power, this is called the power rule for partial fractions. You guys have tons of power rules in here. And it's in your calculus textbook on page 323. But let me give you the gist of it. If you've got some big fraction, and you notice, first off, this is a classic fraction. Look at this problem. It's the integral of 3x squared plus 5 divided by x minus 2 squared plus times x plus 1. You will notice that is a proper fraction. The degree of the top is what? What's the degree of the numerator? 2. What is the degree of the denominator? It's actually 3 because of the x minus 2 squared, that's an x squared. There's an extra x, that grand total of x2 cubed. When you pull it out, it's a degree 3 polynomial. So degree of the top is less than degree of the bottom, proper fraction. And they went ahead and factored it for you. So, but when you got one of these big fractions and you happen to have one of these factors to a power, so you got x minus some kind of constant or whatever, and it's actually raised to, I'm just going to pick a different power. And you got some other stuff being multiplied times that no one cares here. But I'm going to focus on what we call the power rule for partial fractions. See, because here's the deal. When you bust up this common denominator, all the different factors of the common denominator have to be represented by a fraction. And when you have a power, the problem is the term x minus c with that power has to be there, and any factors of this guy. What is a factor of x minus constant cubed? Well, a factor of that would also be x minus a constant squared. And a factor of x minus a constant squared would also be a factor of x minus a constant. So not only does the power, the factor of x minus c to that actual power has to be there, but all powers below him, down to 1, has to be there. This is part of the quote-unquote power rule for partial fractions. But it gets better. These guys are connected. They're all the same factor, they just have different powers. Look at the smallest power. It's x minus c to the first power. Now, according to the rules of partial fractions, this thing has to be a proper fraction. A proper fraction means the degree of the numerator has to be less than the degree of the denominator. This degree is 1. What is the degree less than 1? 0. And a degree 0 polynomial is called a constant. So this guy, I'll just call him big C, he's kind of a special C there, just don't get confused with that little C down there. This guy is going to be a constant. But because all these guys are cut from the same mold, since this guy is a constant, the power rule says all the other factors that are raised, that have this factor raised to a power will also have the same style numerator, which would be a constant. So this one's going to be a constant here. This one's going to be a constant here. So you get a constant over x minus c cubed, constant plus a constant over x minus c squared, plus a constant over x minus c. So let's extend that over a little bit. Let's say, for example, I happen to have some kind of degree less numerator, and over here I've got some factors, and one of my factors happens to be something like that, x squared plus x plus 1, and I'm going to say it's squared over here. And I want to bust this thing up over its partial fractions. Well, you have your other terms, but I'm focusing on this guy in terms of the power rule. In terms of the power rule, this factor, even though it's got a power, this is a factor of your common denominator, has to be there. X squared plus x plus 1 squared. And according to the power rule, any lower powers also have to be there. So instead of x squared plus x plus 1 squared, it's got to be there. Also, x squared plus x plus 1 to the first power has to be there. That power and any powers all the way down to 1, those factors also have to be there because they're all factors of the big power. But let's see if you learned anything from last time. Look at the smallest power here. It is the x squared plus x minus 1, plus 1 to the first power. Since this guy is a quadratic, what style the numerator is this guy going to have to be a degree less than a quadratic? It has to be linear. So linear would be something like cx plus d. It's going to look like a cx plus d because this is degree 2 squared. This has got to be a degree 1 linear. And since this guy was linear, this guy, even though he's a squared power here, is still going to be linear. It's going to be ax plus b. This concept, and of course you got your other factors being part of your partial fractions there as well. But just this is the rule for the power rule for partial fractions. So let's take a look at this problem here. I've got this problem, 3x squared plus 5 divided by x minus 2 squared times x plus 1. I want to bust this guy up. Well, the first thing I'm going to pull off is the factor that doesn't have a power. What's the factor that doesn't have a power on him? It's understood power 1, of course. It's x plus 1. Now, the x minus 2 squared, I'm going to use the power rule on that. And the x minus 2 squared, it's got that factor has to be there, x minus 2 squared, and any other lower powers of this factor. What's a power lower than x minus 2 squared would be just x minus 2, officially to the first power. Now, since this guy is a linear term, the numerator has to be a constant. My favorite letter is an A. Since this guy, the x minus 2, is a linear factor, its numerator has to be a constant. I'm going to call him C, just put them in order. And because these two guys are connected, even though I know you're thinking this guy's square and this thing needs to have a bx plus c, but that's not the power rule. The power rule says these two factors, the numerator is going to look just like each other, and it's based upon what the smallest power did. Since this was a constant, this guy's also going to be a constant. Now, right here is where people will mess this problem up. If you remember your partial fraction techniques, once you bust up the problem and look at the style of what the partial fractions have to be, you got to go back and solve for the A, B, C, or whatever letters you got to solve for here. And to be able to do that, you got to multiply by your common denominator. My question to you is this: what's the common denominator? What's the common denominator? Well, x minus 2 squared times x plus 1. It's this denominator. Where students will mess this problem up is they see these three factors, x plus 1, x minus 2 squared, and x minus 2. And they're going to multiply everything by x plus 1, x minus 2 squared, and an x minus 2. And then they distribute and they get these equations. But then by doing that, your annihilator of one of your terms will actually kill off all the terms, and it doesn't really help you out. You want the least common denominator, which is actually the original denominator of the original fraction that you're playing with. That's what you multiply by. That way you don't screw it up and have problems in trying to solve for the letters. So now, this x minus 2 squared times x plus 1 is what I'm going to multiply by. So when I multiply by this first term, the entire denominator cancels, and you should just be left with the numerator. 3x squared plus 5 equals here, the a over x plus 1 cancels with the x plus 1, so those guys cancel, and you're left with a times x minus 2 squared, plus here the x minus 2 squared is going to cancel, and you're left with b times x plus 1. But look at c. You got c divided by x minus 2. You're multiplying it by x minus 2 squared times x plus 1. Well, x minus 2 and the x minus 2 squared, one of those is going to cancel, but you're left with a c with still one left over, x minus 2 times that x plus 1. Does that make sense? Now, you go and do the annihilator method on this problem. So, how many letters am I supposed to solve for on this problem? 3. I need 3 letters, 3 numbers for x. X equals, x equals, x equals. I'm solving for A, B, and C. I want 3 x numbers. What x numbers do you suggest I use? Always do the annihilators first. It gives you answers immediately. What numbers would you use? I would use 2, 1, watch out, -1. The 0 of x plus 1 is actually -1, so I would use 2, -1. The problem is, when you look at these factors, there's only 2 annihilators. There's only 2 zeros of these guys, 2 and -1. So what number am I going to pick for my third guy? Because I have a brain, I choose 0. You can choose anything you want to, it'll work, but save myself tons of time, I'm going to put 0 in this thing. So now I'm going to plug in 2 in for all the x's. 2 squared, 4, times 3, 12, and 12 plus 5 is 17. Equals a times 2 minus 2 is 0, squared still 0, plus b times 2 plus 1 is 3, plus c times 2 minus 2 is 0, and 2 plus 1 is 3, and 0 times 3 is still 0. So these terms go away. So I got 17 equals 3b. b is equal to 17/3. One letter down, 2 to go. X equals -1, plugging it in. It's an annihilator, so that will solve for one of my letters. -1 squared is 1, times 3 is 3, plus 5 is 8, is equal to a times -1 minus 2 is -3 squared, plus b times Negative 1 plus 1 is 0, plus c times negative 1 plus 1 is 0, times negative 1 minus 2 is negative 3, but 0 times negative 3 is still 0. So this time the b and the c are gone. But be careful, negative 3 squared is 9, so I get 8 equals 9a. So a is equal to, divided by 9, 8 ninths. Now, 0 was not an annihilator. And because of that, when I plug him in, I'm going to get a big equation with all the letters. But now I got my annihilator numbers, I can go back and substitute. So here we go. Plugging in 0, 0 squared is 0 times 3 is still 0 plus 5 is 5, is equal to 0 minus 2 is negative 2, squared makes it 4. Go ahead and do that math, 4a. Plus 0 plus 1 is 1, 1b. Plus 0 minus 2 is negative 2. 0 plus 1 is 1. 1 times negative 2 is negative 2, so it becomes minus 2c. So I've got 5 equals 4a plus b minus 2c. Now, these are crappy fractions, but that's real well-worked problems for you guys, so nothing ever works out, answers 2. No, it doesn't work out like that. So I'm going to plug in crappy fractions here, but I'm going to show you guys quickly on how to get this problem done. So this is 5 is equal to 4 times a is 8 ninths, plus b, which is 17 thirds, minus 2c. So 5 equals, now this is why I allow calculators. So just to make sure we don't screw this thing up, I'm going to put this problem on my calculator here. This is 4 times 8 ninths. Well, 4 times 8 is 32, so you're right, that's 32 ninths. Plus 17 thirds. And I get 9.22222, which converts to 83 ninths minus 2c. This over the lights, you got to see a little better. There you go. Now, how are you going to solve for c? What's your next move? Just don't make careless errors. What's your next move? I would subtract 83 ninths. You got it. And there'll be 5 minus that answer of 83 ninths. And I end up getting negative 38 ninths equals negative 2c. And then what's your last move? Divide by negative 2 on both sides. So divide that by negative 2. And on the new operating system, once you're in fraction mode and you keep doing the arithmetic, it stays in fraction mode. I end up getting 19 ninths for c. So, especially with crappy fractions, if I have access to a calculator, I shall use it. So, here again is a place where students will screw this problem up. The inability to recognize a letter and replace it with a number. They put the wrong number over the wrong letter or something or other. I've seen amazing things what people do here. So this will turn into the integral of, just be careful, a is 8 ninths. That'll be 8 ninths divided by x plus 1, plus b is 17 thirds, divided by x minus 2 squared, plus c is 19 ninths, divided by x minus 2 dx. So now the ultimate goal in now integrating this guy is integrating each term. Now 2 of these terms should be rather quick. So what's the integral 8 ninths divided by x plus 1 dx? What do you get for this guy? That'll be 8 ninths, what? Natural log, absolute value of x plus 1. And for the guy in the back, the 19 ninths divided by x minus 2 is going to give you what? That'll be plus 19 ninths natural log absolute value of x minus 2. And then one big old plus c for your answer. The problem is the middle term. Now again, this is u substitution in your head. That's what we want. U equals the denominator, du equals dx. And then you get 1 over u, which is natural log absolute value of u, natural log absolute value of x plus 1, natural log absolute value of x minus 2, with the constants out front. But with the guy in the middle, because he has a power, you've got to rewrite him. So this part turns into 17 thirds times the integral of x minus 2 to the negative 2 dx. Because he has a power, you don't want the power in the denominator, you're going to bring it to the numerator and make the exponent negative. Now, to be able to integrate this guy, it is a traditional u substitution. U would be equal to x minus 2, du equals dx. So when you substitute, this becomes 17/3, the integral of u to the negative 2 du. So when I integrate that, that will give you 17/3 u to the add 1, negative 1 over negative 1 plus c. So when I clean that up, that gives you negative 17 over 3u. And the last thing I'm going to do is back substitute. That's going to give you negative 17 over 3 times u, but u was x minus 2. So that answer goes right here, and it becomes minus 17 divided by 3 times x minus 2, and this is my result. So this tells me that the integral of that 3x squared plus 5 divided by x minus 2 squared times x plus 1 is going to be 8/9 natural log absolute value of x plus 1 minus 17 over 3 times x minus 2 plus 19/9 times natural log absolute value of x minus 2 plus c. Question? Yeah. This thing over here? Okay. Yes. This, right. This one over here is because inside the parentheses is a quadratic, x squared plus x plus 1. Then the numerator, well, again, your partial fraction rule is you got to have the x squared plus x plus 1 to whatever that power is on the outside, and then all powers below that. And then you get an x squared plus x plus 1 officially to the first power. But because this was a quadratic, the numerator has to be a degree less. Degree less than a quadratic, degree 2 is a degree 1. Degree 1 is that linear cx plus d. So if this one is cx plus d, even though this has a squared power on it, the inside, those parentheses, are the same, and this is part of that Dr. Stewart's power rule for partial fractions. All the numerators of the like terms are going to be the same. So you're still going to get different letters, of course, ax plus b, but it's still going to be a linear term because it's coming from what's inside the parentheses. That's the power rule. And this will be the worst case you ever have. But again, this stuff is very important because not just this class, but there's differential equations after this class, and especially for you electrical engineers, I'm going to pick on especially, you're going to beat this thing to death in your circuits class. This idea of taking big fractions and breaking them up into partial fractions. Okay, but all the rest of us majors have to do it as well. All right. We'll turn the page. How many rules I made you memorize so far? That's sad. You should know. 17, actually. 17 formulas for integrals. 17. There were the 14 original formulas. There were the 3 from the k rule. You remember e to the kx dx is 1 over k, e to the kx, the integral of the cosine of kx, and the integral of sine of kx rules. So there are 17 rules. Well, here you go. We're up to number 18 now. Rule number 18. Now, this is a deviated version of what you had memorized from basically Calculus 1, and that was the integral of 1 over 1, or x squared, plus 1 dx. What was the integral of 1 over x squared plus 1 dx equal to? What was the formula? Arctangent of x plus c. But what if, instead of a plus 1, you had a different constant? Well, we're going to call that, instead of plus 1, we're going to call it a squared. So you end up, in place of x, I'm going to put a u, because I'm going to rewrite this as u substitution. But u is equal to x, so you got the u squared plus, instead of a 1, you can call it a squared. And this deviates the verse. It's still arctangent, tangent inverse, but this is how it affects it. The integral of 1 over u squared plus a squared du is 1 over a times the arctangent, or tangent inverse, of u divided by a. So it affects the coefficient up front, and it affects the angle on that trig inverse problem, plus c. So this is the formula here. Now, so here's the problem here. This one right here, the integral of 1 over x squared plus 9, this is one you could probably do in your head. And most people do, but they typically screw this problem up once I make them a little bit tougher. They'll get this one right. And this one, this is the same thing as integral of 1 over x squared plus 3 squared. and dx. And if I use this rule, you can see the answer is going to be, well, a is going to be 3. A squared is 9, so a is 3, so this will be 1/3 tangent inverse of u, which is x, over a, which is 3 plus c. And you're right. You can look at it and tell what the answer is. But if you wanted to show your work properly, we wrote this formula in the guise of u substitution. So to show your work, because trust me, I'm going to make this stuff nastier later, that I would, quote, start with the u squared. U squared is x squared. That makes u equal to x, and that makes du equal to dx. Also, the a squared is 9 from the formula, making a equals 3. So when you substitute, this will turn into 1 over x squared is u squared. Then the 9 is a squared. And the dx becomes du, keeping up with that constant. And then this is the formula 1 over a arctangent of u over a plus c. And then you back substitute 1 over 3 arctangent u, and u is x, over a, which is 3 plus c. And you got it if you just looked at the problem, but this technique right here, using that u substitution, is most important, because it doesn't take much before the problems start messing up. Take a look at the next guy. This is the integral of 1 over 4x squared plus 9 dx. Now, let me put it into the guise of these kind of problems. This section is called partial fractions. So we're looking at trying to bust up denominators. The problem is, this is that u squared plus a squared look. U squared plus a squared doesn't factor. U squared minus a squared, yeah, if it was a minus, that's the difference of squares. U plus a, u minus a, and I can use partial fractions on that. But because this is a plus, it's not going to factor. So this guy has a special rule. And that special rule is memorizing this, the integral of 1 over u squared plus a squared du is equal to 1 over a arctangent of u over a plus c. That's my rule. But to do this problem, here's the deal. In this problem, the u squared, that's going to be your variable. That's going to be the 4x squared. The a squared part's your constant. That'll be 9. That makes u, what is it? If u squared is 4x squared, what does that make u equal to? What do you got to do? You got to take the square root of both sides, and that would be 2x. And if a squared is 9, take the square root, a equals 3. But here's the deal. This formula is u substitution. How do you do u substitution? You figure out what u is, and then what's your next move? Du. Take derivative. What's derivative of 2x? 2 dx. Solve for the dx because you're going to substitute in for it. So divide by 2 on both sides. So now you get a constant. 1/2 du equals dx. So when you substitute into this guy, this will turn into the integral of 1 over the 4x squared is u squared plus the 9 is a squared. However, the dx is going to get replaced with 1/2 du. Constants get to go where? Out front. So you got this extra 1/2 times that integral of 1 over u squared plus a squared du. This becomes 1/2 times the formula 1 over a arctangent of u over a plus c. And then with classic u substitution, after I integrate it, what do I have to do? Back substitute. So this is equal to 1/2 times 1 over a is 3, times the arctangent of u is actually 2x over a, which is 3, plus c. And then, of course, the last thing I'm going to do here is clean up my fractions. What's 1/2 of a third? 1/6. So I got 1/6 times the arctangent of u, which is 2x over a, which is 3, plus c. And there is my integral. Does that make sense? It's really, this formula is designed with the u substitution concept in mind. And this is actually giving you a hint of what you're going to see in the next section, which is section 6.4, which is table integration. Table integration is based upon the number one technique of integration, U substitution. So the formula is always written in terms of U with the du stuff. All right, turn the page. All right, so what ifs? We have been working with integrating fractions. And if you remember with your partial fraction techniques, you've got an integral of a big old fraction. First things first. If I'm trying to integrate a fraction, first thing I'm going to do is let u equal to the denominator. Then du, if it's in the problem in numerator, du is in the problem, dx there. And if it turns into, 1 over u, then I'm good to go and integrating it. But what if u substitution doesn't work? Well, number one, u substitution doesn't work. It had to be a proper fraction where the degree of the numerator was less than the degree of the denominator. And third thing to use partial fractions is the denominator had to factor. What if case number 2 doesn't hold? The degree of the numerator is the same or bigger than the denominator. So notice in this problem, the x squared minus 5x plus, x to the fourth minus 5x squared plus x minus 7 divided by x minus 2. This guy right here, you clearly see the numerator has a degree bigger than the denominator. If the numerator is the same or bigger than the denominator, this is what you have to do. You've got to do something you did back in the 10th, 11th grade here, long division. You're going to have to divide this guy out. So, and remember about long division with polynomials. If there is a term missing, you got to put a 0 in for it to make sure all this stuff lines up. Otherwise, you screw the problem up for sure. So, in this problem, just to get used back to the terminology here, this is x to the fourth minus 5x squared plus x minus 7 divided by x minus 2. The dividend is the numerator. The divisor is the denominator. So my divisor is x minus 2. My dividend goes inside my bracket here, and it is, notice something, brother, there's a term missing. It's x to the fourth, but there is no x cubed term. So you put plus 0x cubed minus 5x squared plus x minus 7. If you got a term missing from the degree term all the way down to the constant, you put zeros in there. So now we're going to play the long division game. Long division, this goes back to third grade, except we're dealing with polynomials instead of numbers, but the concept is the same. What times x is x to the fourth? X cubed, and you put that up here in the quotient spot, x cubed, and then you multiply and distribute. X cubed times x is x to the fourth. X cubed times a minus 2 is minus 2x cubed. Now, the process is long division. After you multiply and you put it down below, then what do? Other way around. You subtract. You subtract them, and subtracting changes the sign. So I'm going to subtract, and this becomes a minus, this one comes a plus. So in my notation, I always put the sign above it. So that's now my new sign because a negative will change your signs. So, and notice something rather, the first term will always cancel. If it doesn't, you really screwed it up. And then I got plus 0x cubed plus 2x cubed is 2x cubed. And then I'll bring down my next victim, minus 5x squared. And then I play the game all over again. What times x is 2x cubed? Plus 2x squared. And then now I'm going to take the 2x squared and multiply by each term in my divisor. 2x squared times x is 2x cubed. 2x squared times minus 2 is minus 4x squared. But now what am I going to do? Subtract, which changes my signs. Minus, this becomes a plus. And the first term, 2x cubed minus 2x cubed, should cancel. And you're left with minus 5x squared plus 4x squared leaves me with a negative x squared. I bring down my next victim, plus x. And I play the game all over again. What times x is negative x squared? Negative x. So a negative x times a positive x is a negative x squared. A negative x times a negative 2 is a plus 2x. But then what do? Subtract, catch a pattern. Subtract, which changes my signs. This becomes a plus, this becomes a minus. The first term, minus x squared plus x squared cancels. Then I got plus x minus 2x is minus x. Bring down my next victim, minus 7. Play the game all over again. What times x is negative x? Negative 1. Negative 1 times x is negative x. Negative 1 times negative 2 is plus 2. But then what do I have to do? Subtract, change my sign, so this minus x becomes a plus x, and plus 2 becomes a minus 2. Minus x plus x cancels, but now I have a minus 7 minus 2 makes it a minus 9. And then I ran out of terms, so I'm done. But then you got to remember about how to write your answer. When you do long division, whether it be third grade or high school, the answer is in two parts. You got what we call the quotient answer and the remainder answer. This above the radical, this is your quotient. This is the actual answer, but this minus 9 is the remainder. And remember, with a remainder is a fraction of your answer, and you got to write it as a fraction. This part goes with a fraction. So the answer is going to end up turning into x cubed plus 2x squared minus x minus 1 plus, officially, negative 9 divided by the original divisor. What were we dividing by originally? X minus 2. So, I mean, you can clean that up and make it look better. That'll be x cubed plus 2x squared minus x minus 1 minus 9 over x minus 2. And there is my resultant. Does that make sense? Now, because here's the big deal. We're in integral calculus class. We got to integrate this thing. So the original problem was integrate x to the fourth minus 5x squared plus x minus 7 divided by x minus 2. Well, anytime the degree of the numerator is the same or bigger than the denominator, you have to do long division and rewrite the way your answer looks. Now I'm going to integrate x cubed plus 2x squared minus x minus 1 minus 9 over x minus 2, and I can do that in my head. Integral x cubed is x to the fourth over 4, plus integral of 2x squared is 2x to the third over 3, minus integral of 1 is, integral of 1x is negative x squared over 2. Integral of minus 1 is minus x, minus 9 times the natural log of the absolute value of x minus 2 plus c. You can integrate the darn thing. But in this form, I could not have integrated. Does that make sense? Long division. But listen to my words. It is when the numerator is the same or higher degree than the denominator. It's not a proper fraction. You've got to make this mixed fraction thing out of it. Long division. Now, a lot of folks come after class, hey, Dr. Taylor, because you were dividing by x minus 2, couldn't you have done some kind of a synthetic division on this thing? Yes, you could. But synthetic division is very specialized. To use synthetic division, you have to divide by x minus constant, okay? And in this example, that's what we got. And the next example is what I got. I could have done it there, but wait, I'm going to turn the page in a minute, and they're going to get much nastier. We're doing the easy ones first. So, in 9 times out of 10 of the problems you're going to use, you're going to have to do the long division, because anything other than x minus c, you can't do synthetic division on. You're actually going to have long division. So get used to the long division. So let's integrate this problem here. This is the integral of x squared divided by x plus 4. Okay? So this is going to turn into, well, first you'll notice that I can't integrate this guy because the degree of the numerator is bigger than the degree of the denominator. So I got to use long division. I'm dividing by x plus 4. The numerator is x squared, but there's some terms missing, so I got to put 0 in there. Plus 0x plus 0. Now play the game. What times x is x to the fourth? Excuse me, what times x is x squared? X. X times x is x squared. X times plus 4 is plus 4x. What do? Subtract, changes my signs. First guy cancels. 0x minus 4x is negative 4x. Bring down your next victim plus 0 and play the game all over again. What times x is negative 4x? Negative 4. Negative 4 times x is negative 4x. Negative 4 times negative 4 times a positive 4 is a negative 16. Then I have to subtract, which changes my signs. This becomes a plus. This becomes a plus. The minus 4x plus 4x cancels. and 0 plus 16 is 16. So this problem now is going to turn into the integral of my quotient, which is the x minus 4, plus the remainder is a fraction of your answer. So the remainder is going to be, the remainder is 16, so that's your numerator divided by the original divisor of x plus 4. So all this beautiful work, I actually didn't do anything except, 10th grade long division. But now the problem of x squared divided by x plus 4 has turned into the integral of x minus 4 plus 16 over x minus x plus 4, and which means I can integrate this thing very easily now. The integral of x with respect to x is x squared over 2, minus the integral of 4 with respect to x is 4x, plus the integral of 16 divided by x plus 4 with respect to x is 16 natural log absolute value of x plus 4 plus c. And there's my result. Makes it a very quick integral once you get it in the right format. Long division. Okay? So let's do this problem here. The integral of x cubed minus 4x minus 10 divided by x squared minus x minus 6. First thing when I'm looking at this problem is automatically I see that degree of the numerator is bigger, the same or bigger, this was bigger, because degree 3, than the denominator, which means long division. The divisor is x squared minus x minus 6, but look at your dividend, your numerator. There's a term missing. Pay attention to that and don't forget to put a 0 in for the term missing. This is x cubed. There is no x squared term, so plus 0x squared minus 4x minus 10. Now play the game. What times x squared is x cubed? X. X times x squared is x cubed. X times minus x is minus x squared. X times minus 6 is minus 6x. I distribute my term, my x throughout. I subtract, changes my signs. The first term, x cubed minus x cubed cancels. 0x squared plus x squared is x squared. Minus 4x plus 6x is plus 2x. I bring down the next victim, minus 10, and play the game again. What times x squared is x squared? 1. So I distribute the 1. That gives me 1x squared minus x minus 6. Multiply by 1 is rather easy there. Then I got to subtract, which changes my signs. Minus, plus, plus. First term cancels, x squared minus x squared. Then I'm left with 2x plus x is 3x. And minus 10. Minus 10 plus 6 is minus 4. So now this problem has turned into the integral of x plus 1 plus your fraction, your remainder, which is the 3x minus 4 over the original denominator x squared minus x minus 6 dx. So this problem has turned into this problem here. But now I can integrate x, no problem there. That's x squared over 2. I can integrate 1 with respect to x. That's x. My problem is this guy. So now I've got to work on this. Now this remaining fraction is a proper fraction. Degree of the top is less degree of the bottom. But did you notice that the denominator factors? So this is x minus 4 divided by x squared minus x minus 6 factors into x minus 3 times x plus 2. So this guy, I get to use my partial fraction technique. So I'm going to bust him up over its common denominator of x minus 3 and x plus 2. Since both of these guys are linear, the degree less than that would be constant, so I have the a and b in my numerator for these guys. I'm going to multiply my entire equation by my common denominator of x minus 3 times x plus 2, which will completely cancel here. I'm left with 3x minus 4 equals a. Here the x minus 3's cancel, so you're left with a times x plus 2 plus b. Here the x plus 2's cancel, you're left with x minus 3. How many letters I got to solve for? 2. So pick 2 x's. What numbers you suggest I'd use? The annihilators. I'm going to choose negative 2 and 3. So x equals 3, x equals negative 2. I'm going to plug it in. 3 times 3 is 9. 9 minus 4 is 5. Equals 3 plus 2 is a 1. Try again. 3 plus 2 is 5. Times a is 5a. Sorry, I see the answers in my head. I can't help myself. All right, keep going. Plugging in -2. 3 times -2 is -6. Minus 4 is -10 is equal to -2 plus 2 is 0, so that term's gone. -2 minus 3 is -5, -5b. Now solving, I'm going to divide by 5 and get a equals 1. And I'm going to divide by -5, -10 divided by -5, and I get b equals 2. Now, you're going to see a problem on your second test, because this stuff's not on your first test. So what will this problem turn into? Yeah, I'm not going to integrate it yet. I'm going to wait to integrate the darn thing at the end. I want to see what this guy's going to bust into. So now this problem will turn into the integral of the original quotient, which is x plus 1 plus your partial fraction. Now, a was 1, so this is 1 over x minus 3, plus b, which is 2 over x plus 2 dx, just replacing the fraction part. So this becomes my resultant integrand. So this is the integral of the problem after we beat it to death in terms of breaking it up over long division and partial fractions. Now, give me the solution. Integrate. Integral of x is x squared over 2, plus integral of 1 is x, plus integral of 1 over x minus 3 is natural log absolute value of x minus 3, plus integral of 2 divided by x plus 2 is going to be plus 2, natural log absolute value of x plus 2. No bounds on this stuff, so 1 big plus c. So you'll see when I get you to with your next test, I'm going to give you a problem like this, but I'm going to ask for after long division, what's the integrand? So I gave you this problem. After long division, what's the integrand? After the partial fraction, what's the integrand? And don't forget, you still got the first two terms there. You're only doing the partial fractions on the last integral, on the last fraction there. And then what's the solution? Well, what if we are working with this stuff and I got a quadratic that doesn't factor? Can I still integrate the darn thing? Question. Yeah.
I was going to ask, if the denominator is missing a term, what you filled in with the 0?
Yes. If there's any term missing in the numerator, dividend, or the divisor, either one of those, you got to put a 0 in for it and do the long division stuff. All right. So what happens if I got a quadratic that doesn't factor? Can I still integrate the darn thing? Yes. But the trick is going to be something you guys learned in high school and hated, called complete the square. Now, when you complete the square, the purpose of this complete the square is to take some kind of crappy polynomial, I call him ax squared plus bx plus c, and turn him into this u squared plus a squared look. And you've seen that u squared plus a squared denominator, you get that arctangent mess out of it. But you've got to complete the square off this guy to turn him into this proper term. Now, if the quadratic expression is x squared plus bx plus c, this means your leading coefficient happens to be a 1. The trick on completing the square is this. You take half the b term, square it, and you add it to the x's. The problem with this stuff is it's not an equation. You know, what I do to one side, I do to the other. I don't get to do that. I've only got one side. This is an expression. So remember these words. If you giveth, you must taketh away. Maintain equality. Okay? So, to complete the square, you have to take half the b term, and that b term is the coefficient from the x, which comes from the quadratic formula. So in this problem here, x squared plus 6x plus 13. We're going to complete the square on that guy. You'll notice that the coefficient from the x squared is a 1. So here it is. This is x squared plus 6x. Leave a little space. You're completing the square on the x's. And then put the plus 13 over here. To complete the square, you take half the b term and square it. That gives you your magic number. What is the b term in this problem? 6. So we're going to take half of 6, half times 6, and square it. What's half of 6? 3. And what's 3 squared? 9. The magic number is 9. And I'm going to take this number, 9, which is my complete the square number, and I'm going to add that number to the x's. But this is an expression. This is the number I add to the x's to complete the square off the variable, but then I got to take away that same number off that constant. that constant is your kind of your garbage collection agency. Whatever you throw in, this is what you're going to be throwing out, okay, to maintain equality. Add 9, subtract 9, some 0, so you're not changing the problem. But now, this quadratic x squared plus 6x plus 9 part's going to factor, not just factor anyway, it'll factor perfectly. How does x squared plus 6x plus 9 factor? X and x, what times what is 9? That adds up to be 6. 3 and 3, your signs will be the same. They're both pluses. And then you got to pretty much put your constants together. What's 13 minus 9? Plus 4. So the problem turns into an x plus 3 squared plus 4. You've completed the square. And now, with your denominators looking like this, you can do an arctangent route on that with the u substitution stuff. So, on this particular problem here, if we completed the square, x squared plus 2x, leave a little space, plus 10, what is the number that's going to complete the square off this guy? You take half the b term and square it. What's your b term in this problem? 2. What's half of 2? 1 squared is what? 1. The magic number is 1. So I'm going to add 1 to the x's, and I'm going to take away 1 from the constants. You give it, and you take it away. But now this quadratic x squared plus 2x plus 1 factors into x plus 1 times x plus 1 plus 9 minus, 10. 10 minus 1 is 9. This turns into x plus 1 squared plus 9. So now my problem is 1 over x plus 1 squared plus 9 dx. So this problem, which was originally a quadratic, now you complete the square, so you can use the arctangent formula. 1 over u squared plus a squared du is 1 over a arctangent of u over a plus c. Just to remind you your formula if you don't have it memorized yet. Here, u squared would be the x plus 1 squared. That makes u equal to x plus 1, and that makes du equal to dx. A squared equals 9, makes a equal to 3. So when I substitute into this guy, this turns into 1 over, your constant's 1, over u squared plus a squared. But this was a nice problem. Dx is du. So this turns into the actual formula of 1 over a arctangent of u over a plus c. And what's the last thing I'm going to do to integrate this guy? Back substitute. What was a equal to? 3. So this answer is going to be 1/3 the arctangent of u, which is x plus 1 over a, which is 3 plus c. Next time, when we get after our test, I'm going to go back and look at this complete the square and tell you guys, because you'll see this more often, what happens when you have a constant in front of the x squared and how to do a little more deeper completing the square off those guys. But this is a very important technique, and you'll see why when you see section 6.4. So study hard, but study for the test, and I'll see you guys at 2 o'clock at the review session when we go over the homework set. See you guys then.
I'm really sorry for being late, sir.